Welcome to Module 07 of the Data Center Fire Protection Masterclass. This module focuses on sprinkler, dry pipe, and preaction systems, and how water-based protection is applied across data halls, plant rooms, support areas, and other protected zones. The central idea is that system selection is not one-size-fits-all. It should reflect the hazard, the environment, the requirements of the authority having jurisdiction, or AHJ, and the owner's risk policy. We'll compare wet pipe, dry pipe, and preaction arrangements, then connect those choices to practical room strategy. We'll also examine the details that make a system dependable in service, including valve trim, release logic, and supervised points. Finally, we'll consider the evidence needed to demonstrate performance and readiness: hydraulic information, obstruction checks, trip testing and inspection, testing, and maintenance records. By the end of the module, the goal is a clear, defensible approach to choosing and supporting water-based fire protection for different data center spaces. This module focuses on the water-based suppression backbone of data center fire protection: sprinkler, dry, and preaction systems. The central challenge is to engineer, supervise, test, and maintain these systems without compromising data center continuity. I'll begin with the protection strategy, then distinguish wet, dry, and preaction systems according to room risk and environmental conditions. We'll also examine riser, valve, and zone architecture, sprinkler layout, obstruction control, and the logic behind trip, water flow, tamper, and low air supervision. The intended audience includes owners and facility teams, fire protection and MEP engineers, commissioning agents, specialist contractors, BMS and fire alarm integrators, and AHJ or insurer reviewers. By the end, participants should be able to select an appropriate system by room, challenge the hydraulic and layout basis, and build credible testing and restoration evidence. The module also connects fire alarm cause and effect logic with physical suppression and water damage governance, supporting design review, FAT, SAT, IST, operating drills, and lifecycle inspection, testing, and maintenance aligned with NFPA 13, NFPA 25, and FMDS 5-32. This module presents a complete path for developing and operating a data center fire protection system, from the initial strategy through long-term readiness. The central idea is to connect every design decision with clear evidence that the system will perform when needed. We begin with strategy and standards, including the water-based fire control philosophy, the authority hierarchy, and the basis for selecting protected rooms. Next, we examine system architectures, comparing wet pipe, dry pipe, and preaction arrangements, along with valve trim, nitrogen systems, and monitored interfaces. The third section focuses on layout and engineering. That includes sprinkler placement, obstruction control, hydraulic design, seismic supports, and measures that reduce the risk of water damage. We then move into testing and commissioning, covering factory and site acceptance testing, integrated system testing, trip tests, water flow and tamper signals, low air conditions, and restoration evidence. Finally, we address operations and lifecycle management, including NFPA 25 style inspection, testing and maintenance, impairment control, response playbooks, workshops, and key takeaways. The training method follows the system visually, from protected spaces to valve logic, hydraulic evidence, and integrated test scripts. This module takes a sprinkler concept and turns it into a protection system that can be reviewed, tested, and maintained in operation. The learning path follows 5 connected decisions. First, we define the hazard area by considering room risk, water sensitivity, and environmental exposure. Next, we select the system type, whether that is wet, dry, single-interlock preaction, or double-interlock preaction. We then establish valve logic, including supervision, release criteria, water flow, and reset. From there, we develop the layout and hydraulic evidence, covering sprinkler placement, obstructions, the design area, and the available water supply. Finally, we document proof and inspection, testing, and maintenance, including trip tests, impairment controls, and supporting evidence. The design outputs include a room-by-room protection selection table, riser and valve set architecture, sprinkler and hydraulic documentation, and a supervised point schedule. The operations outputs go further, providing test scripts, integrated FACP, BMS, and SOC response evidence, an NFPA 25 style IDM calendar, an impairment workflow, and a reset and return to service checklist. The goal is a complete, traceable system from design through operation. Module 07, Section A, focuses on strategy and standards for selecting fire protection systems in data centers. The central idea is that system selection should never be automatic. It begins with 4 considerations: the hazard, the environment, water sensitivity, and acceptance by the authority having jurisdiction, or AHJ, and the insurer. This section has 3 outcomes. First, we'll define where water is needed immediately, and where controlled water entry may be justified. Second, we'll treat dry systems as special exposure systems, rather than assuming they are the default choice for condition data halls. That distinction is important because system type should reflect the actual exposure and operating environment. Finally, we'll look at how to keep active suppression available when it is needed. That requires effective supervision, inspection, testing, and maintenance, along with disciplined impairment control. In other words, protection is not only about selecting equipment. It also depends on keeping the system monitored, maintained, and ready to operate. The goal is a defensible strategy that balances suppression performance, water concerns, and operational acceptance. This slide establishes the hierarchy we use to make fire protection decisions traceable and defensible. At the top is insurer and owner risk, supported by FM Global DS 5-32, TIA 942, and the owner's policy. These requirements shape the expected property loss protection, availability objectives, and the specific pre-action configuration. Next, the system lifecycle is governed by NFPA 25 and the equipment manufacturer's manuals. That layer defines inspection, testing, maintenance, and the owner's responsibilities after installation. The alarm and integration layer then relies on NFPA 72 and NFPA 3 and 4 to control water flow and supervisory signals, releasing interfaces, and integrated systems testing. Sprinkler design itself follows NFPA 13, the adopted SNI requirements, and the project's design basis report. These determine installation, spacing, and water supply. Finally, legal and brigade requirements, including PERMEN PUPR and local damper conditions, govern approval, access, and impairment notifications. The key principle is simple. Every design choice must trace back through this hierarchy. We should never use an unlisted bypass or release delay merely as a shortcut to avoid water damage. This slide presents the integrated suppression system and its core objective. The goal is not simply to use no water. It is to achieve fast fire control with acceptable collateral damage and recoverable operations. That distinction is important because effective protection must limit both the fire itself and the disruption caused by responding to it. The first layer is mechanical, shown in red. Its purpose is to control the fire quickly, before it can spread across cables, racks, or plant compartments. The second layer is digital, shown in orange. This includes detection logic, release sequences, and supervision through the SOC, confirming what is happening in the field and supporting the correct sequence of action. The third layer is supervisory, shown in green. Nitrogen, or N2, pneumatic regulation helps expose hidden leaks and prevents internal corrosion. Together, these layers form one coordinated system rather than 3 separate functions. Mechanical control handles the physical event, digital systems manage detection and release, and supervisory controls help maintain system integrity over time. This slide provides the system selection logic for wet pipe, dry pipe, and pre-action protection. The key principle is that the selected system must match the fire scenario, water sensitivity, ambient conditions, and restoration model. Wet pipe is typically used in conditioned spaces where freezing is not a concern and immediate water availability is important. Because the piping is already filled, it offers the simplest and most reliable operation. Even so, we need to review water damage exposure and confirm that zones can be isolated. Dry pipe is intended for unconditioned or exposed areas where water-filled piping could freeze. Air or nitrogen pressure holds the dry valve closed until sprinkler operation. It is not normally the default for condition data halls because delivery time and maintenance become critical. Preaction is suited to water-sensitive areas where controlled water entry and detector-supervised release are justified. It is more complex, so release logic, supervision, trip testing, and reset procedures must be clearly managed. For conditioned Indonesian data halls, dry pipe is generally a special exposure decision, while preaction may be appropriate for water-sensitive IT spaces when supported by the fire strategy. Final selection must align with NFPA 13, SNI standards, and the AHJ. The key distinction among these systems is not the pump room, but the listed system valve and what lies downstream of it. The valve and release logic define the system boundary and the response sequence. In a wet pipe system, the riser and branches remain water-filled, so heat opens a sprinkler and water discharges immediately. In a dry pipe system, the piping downstream of the dry pipe valve contains supervised air or nitrogen. An open sprinkler drops pneumatic pressure, trips the valve, and admits water, with no detection input required. Preaction systems add detection logic. In single-interlock preaction, detection alone opens the valve, but a sprinkler still has to operate before water discharges. In double-interlock, both detection and sprinkler operation, or the associated pneumatic pressure loss, are required before water enters the branch piping. For this data center basis, the building riser is wet, while floor-zone double-interlock valves protect dry branches serving data halls, UPS, MMR, and electrical rooms. That choice reduces accidental water entry, but it adds complexity, so delivery time, drainage, testing, listings, and AHJ approval all matter. This slide presents a room-by-room protection strategy, because each area in the facility has a different hazard profile and operating requirement. In the data hall, classified as critical ICT space, the preferred approach is preaction, or wet pipe if accepted by the authority having jurisdiction. The design focus is on airflow, obstructions, rack arrangement, and the logic that releases the system. For electrical and UPS areas, preaction or another option may be selected through hazard analysis. Here, coordination between clean agent and water systems is especially important, along with clear reset governance. Mechanical and plant rooms may use wet, dry, or preaction systems, depending on the equipment. High ceilings, oily environments, and access for inspection, testing, and maintenance all influence the decision. The exposed loading dock may require dry pipe protection where freezing is a concern, with attention to trip time, pipe pitch, and low-pressure supervision. Finally, offices and support areas generally use wet pipe protection, emphasizing coverage, zoning, and egress. The overall message is that protection should be tailored to the room, rather than applied uniformly across the facility. This section focuses on tracing every critical path from its source to the protected space. That means understanding not just where water flows, but also how air or nitrogen, detection signals, supervisory information, and drains move through the system. For the water path, follow the sequence from the fire pump or city supply, through control valves and risers, to zone valves, branch lines, sprinklers, and drains. The air or nitrogen path begins with the packaged nitrogen generator and air maintenance device, then continues through pressure supervision and the dry or preaction piping. The detection and release path includes ASD and spot detectors, the releasing panel, the FACP interface, solenoid release, and the manual release and abort rules. Supervision covers tamper and water flow switches, pressure switches, panel trouble, and power and communication status. Finally, testing and operations evidence confirms system readiness. Review the inspector test, main and auxiliary drains, flow test point, discharge route, valve lineup, impairment permit, trip record, gauge readings, event logs, and restoration checklist. Together, these records show whether the system is correctly configured, testable, and ready to respond. This module focuses on Section B, system architectures, and the way wet, dry, and preaction fire protection systems are designed and supervised. All three systems pursue the same basic objective: deliver water to control a fire. The important differences are what fills the piping, how the valves operate, and how the system confirms that it is ready and responding correctly. The key concept is that the architecture extends beyond the sprinkler heads. I'll be looking at the complete valve set assembly, including the conditions that allow water to flow and the signals that indicate system status. We'll compare water-filled systems with air or nitrogen-filled systems, and then examine detection-controlled preaction arrangements. We'll also connect supervised points to the fire alarm control panel, the building management system, and the security operations center. Finally, we'll consider reset evidence, so a return to normal indication is supported by a clear, verifiable sequence rather than assumed. By the end of this section, the goal is to understand both how each architecture works and how its condition is monitored. This schematic compares 3 sprinkler arrangements and shows their normal standby condition. The color key is important. Red means water-filled, green means air or nitrogen-filled, and orange dashed lines represent a detection or release signal. The wet pipe arrangement keeps the riser and every floor branch water-filled, with a floor control assembly at each level. The dry pipe arrangement uses red water only up to the dry pipe valve. From that valve upward to the roof and end sprinklers, the piping is green and filled with air or nitrogen. Both arrangements include alarm check equipment and an alarm gong. The floor zone double-interlock preaction system is organized differently. Each PAV, or listed preaction water control valve, serves one floor and has a dedicated release panel and nitrogen generator. The riser is red up to the PAV, then green downstream under normal standby conditions. The key distinction is the zoning and dedicated release package for every floor PAV. This is a schematic of normal standby only. Actual valve locations, final zoning, hydraulic performance, and delivery time require project-specific design and AHJ approval. This section covers the wet pipe sprinkler system, a reliable baseline when the surrounding environment permits water-filled piping. The defining feature is that the piping remains continuously charged with water. When heat from a fire opens an individual sprinkler, water discharges immediately, while the water flow switch reports confirmed flow to the fire alarm control panel or supervising station. The alarm check valve and trim manage the associated flow and pressure behavior, and the main drain and inspector's test connection provide a practical way to verify system operation. In a data center, wet pipe is often appropriate for support areas, corridors, offices, plant rooms, and conditioned utility spaces, provided the risk of water damage is acceptable. It may also be considered in data rooms when approved by the risk strategy and the authority having jurisdiction or insurer. Zoning should support compartmentation and operational response. Before acceptance, I would confirm the hazard classification, review obstructions around racks and cable trays, verify that control valves are locked open and supervised, and check access to flow tests, safe drain discharge, and inspection, testing, and maintenance routes. These checks align with NFPA 13 and NFPA 25. This slide explains the purpose and operating sequence of a dry pipe system. In normal conditions, the system piping is maintained at regulated nitrogen pressure, while fire water remains below the dry pipe valve. The nitrogen connection is on the system side, supplied through a filter and regulator from a packaged nitrogen generator. When a sprinkler opens, nitrogen vents from the piping. That pressure drop trips the dry valve, allowing water from the fire pump header to enter and flow toward the open sprinkler. Tamper, water flow, low nitrogen, and inspector test or drain arrangements support supervision and testing. The key point is environmental protection, not damage control. Dry pipe is primarily intended to protect against freezing, and it should not be treated as the default choice for conditioned data halls, because water delivery is delayed. Engineering review must address delivery time, nitrogen generator cycling, and trapped condensate that can contribute to corrosion. Required proof includes a dry trip test, a low-air alarm test, and documented winterization records. This section focuses on the design and operating discipline required for dry pipe systems in data centers. The central issue is that dry systems are highly sensitive to maintenance and configuration. Their design must support timely water delivery, prevent trapped condensate, and make supervisory failures visible. Start by confirming the exposure that requires a dry system, such as freezing conditions, unheated areas, or exterior piping routes. Then control the system volume, water delivery performance, and valve room location. Low points need auxiliary drains, and the piping should be arranged to minimize trapped water. Air supply also matters. Use an approved compressor or packaged nitrogen generator with a supervised pressure range. Where permitted and justified, an accelerator or quick-opening device may help reduce trip time. The ITM program should trend nitrogen cycles, pressure recovery, and leakage, while routinely testing low-air alarms. Seasonal draining, dry valve trip and reset verification, and inspection of the heated valve enclosure are essential. Finally, dry pipe is not a water damage prevention strategy. It addresses environmental exposure. Where water entry in a conditioned data hall is the concern, evaluate preaction, and have any delayed delivery risk accepted by the AHJ, insurer, and owner. This schematic shows the normal standby condition for a floor-zoned, double-interlock preaction system. Water is available from the wet building riser and fills the riser and floor takeoff up to the preaction valve, or PAV. The PAV remains closed, while the branch piping beyond it is filled with supervised air or nitrogen from the packaged N2 generator. The critical boundary is the PAV. Red represents water-filled piping up to and through the valve, while green begins on the PAV system side and continues to the sprinklers. The separate green nitrogen supply also terminates at that same system side connection. For release, both conditions are required. Approved detection must operate, and the sprinkler system must operate or lose pneumatic pressure. Only then does the releasing panel actuate the PAV, allowing water to enter the downstream branch. This drawing shows normal standby only. After release, water replaces the gas downstream of the PAV. Final trim, nitrogen connection, delivery time, and zoning remain project-specific and require authority having jurisdiction approval. This slide explains the operating logic of a preaction fire protection system, including what it does and what it does not do. The central point is that preaction delays water entry into normally dry sprinkler piping. It does not replace sprinklers or eliminate the need for water-based fire control. Under normal conditions, the piping is maintained with nitrogen or another approved air source, while the preaction valve remains closed. The detection system, release panel, valve trim, control valves, pressure, power, and other trouble conditions are supervised and monitored. During a fire or release event, approved detection activates the releasing panel. The solenoid or pneumatic trim then opens the preaction valve, allowing water into the piping. Only sprinklers exposed to sufficient heat discharge water, while the water flow switch confirms that water is actually moving and initiates the alarm response. A key misconception is that preaction means clean agent, or that it prevents sprinkler operation. It does neither. A single interlock system may admit water before a sprinkler opens, while a double interlock system can delay delivery and therefore requires explicit justification. These principles align with NFPA 13 and NFPA 72. This section focuses on the preaction valve trim and the sequence that allows the system to release safely. The key learning objective is that I should be able to identify every trim component, along with the packaged nitrogen source that maintains regulated supervisory pressure. The system continuously monitors several supervised inputs. These include control valve tamper, low air or nitrogen pressure, water supply and system pressure, release panel trouble and power, and the status of the water flow or alarm line. These inputs help confirm that the system is ready and that abnormal conditions are detected promptly. When a release condition occurs, the system may operate a solenoid or pneumatic release. Depending on the installation, it can also activate a local alarm and water motor gong. Signals are sent to the fire alarm control panel as alarm, supervisory, or trouble conditions, while the building management or data center infrastructure systems receive monitor-only signals. The reset rule is critical. Reset only after the valve, air or nitrogen, drains, detectors, releasing panel, and FACP are all confirmed normal. Always follow NFPA 13, NFPA 72, and the manufacturer's instructions. This slide compares the main preaction interlock types and the logic used to select among them. The choice affects how quickly water becomes available, how well accidental water entry is controlled, and how much effort is required to reset the system. Single interlock systems use detection to open the valve and fill the piping, while sprinkler heat operation is still required before water discharges. They are often chosen when early water availability is important. Double-interlock systems require both detection and a second condition, such as pressure loss or sprinkler operation. That reduces the chance of unintended water entry, but it can delay delivery and add complexity. Non-interlock or special arrangements must be listed, engineered, and explicitly accepted by the authority having jurisdiction or insurer. Detection may use ASD, spot smoke, or heat detection, selected to match the room risk and cause and effect sequence. Manual release, abort, disable, and inhibit functions also require clear design and procedures. Finally, reset is a governed process. Restore detection, valve trim, air or nitrogen supply, drains, controls, and event logs before returning the zone to service, following NFPA requirements and listed panel instructions. This slide shows the pneumatic backbone that supports the dry and pre-action fire protection zones, supervisory nitrogen. The regulator or air maintenance device controls the gas supply, while the nitrogen pressure gauge provides a direct indication of system condition. A low-pressure switch adds an automatic alarm point, and the supervisory manifold distributes nitrogen to zones 1 through 4. The key design principle is that nitrogen is used for supervision, not firefighting. It maintains the required gas pressure in the dry or pre-action piping, helping keep the system normal and reducing the risk of internal corrosion. Water remains completely separate, confined to the fire-water path until system operation requires it. The supervisory arrangement also provides outputs to the supervisory control or building management system. These include low or high pressure, a common fault, power loss, generator run or service alarms, and pressure trending. Finally, commissioning must verify both leakage performance and pressure recovery. In other words, the system has to hold its supervisory condition and recover properly after a demand or test. This design check focuses on one important distinction in the fire protection architecture. The vertical risers remain wet, while only the horizontal floor branches use dry nitrogen pre-action. Water travels from the tank through the fire pump and wet header, up the vertical riser, and to the inlet of each PAV, or pre-action valve. Downstream of the PAV, the bounded floor network is maintained with dry nitrogen. The double interlock arrangement supports the closed sprinklers on that branch and helps limit the presence of water to the area where it is needed. The system boundary is therefore clear. The water-filled path ends at the PAV inlet, and the dry path begins at the PAV outlet and continues through the floor branch to the sprinkler heads. The engineering decision is not to use a dry vertical riser in this example. Instead, each PAV isolates one floor zone, which supports maintainability and helps control potential water damage. The design basis references NFPA 13, NFPA 20, NFPA 25, and FMDS 5-32, where adopted, along with an approved sprinkler architecture. This slide shows a practical method for calculating the physical volume of one dry pipe network, using PAV 2-3 as the example. The calculation starts with the straight pipe volumes for the two network segments. The underfloor distribution contributes 49.2734 gallons, while the ceiling distribution contributes 50.9409 gallons. Together, that gives a straight pipe subtotal of 100.2143 gallons, serving 93 total sprinkler heads. We then add a 10% project allowance for fittings, the valve, and trim that are not yet mapped in the detailed volume model. That allowance adds 10.0214 gallons, bringing the estimated physical volume to 2,357 gallons. At the IFC stage, this allowance should be replaced with actual CAD and OEM component volumes. The decision is based on comparing that result with the INS 500 capacity of 500 gallons for 30 minutes at 40 psi. At 22% of available capacity, PAV 2-3 receives a preliminary pass. The important qualification is that the 10% factor is a project allowance. It is not an NFPA or SNI default, so the final check must use verified project data. This slide shows how we select the nitrogen package by applying two capacity checks, not just one. The first check is the largest riser, which must support the project requirement of 110.24 gallons. The second is total connected volume, which must support 6,061 gallons. Both conditions must pass. The smaller INS 500 and INS 1000 models pass the largest riser check, but fail on total capacity, so they are rejected. The INS 1500 passes both requirements, but with only a 2.3% total margin. That makes it the minimum acceptable selection, rather than the preferred one. The INS 2000 also passes both checks and provides a 98% total capacity margin, so it is the recommended package. The INS 2500 passes as well, but is identified as an option for future campus expansion. The basis for these comparisons is a Potter 30-minute fill at 40 psi, with total capacity calculated using 1.5 psi per 24 hours for new system leakage. The practical lesson is simple. A package is acceptable only when it passes both the largest riser and total volume screens. This slide shows how to calculate and document water delivery time using one witnessed, synchronized clock. The key principle is do not estimate delivery from guest flow. Instead, define the approved test start, record the remote water timestamp, and subtract the two. Here, the approved initiating condition is present at 0 seconds, based on the approved script and synchronized log or video. The valve open diagnostic occurs at 4.8 seconds, but that is diagnostic only. It is not the endpoint for the delivery calculation. The actual endpoint is water at the hydraulically remote test point, recorded at 23.5 seconds through a transducer, flow switch, or witness discharge. The formula is straightforward. 23.5 minus 0 equals an end-to-end delivery time of 23.5 seconds. Compared with the adopted 30-second limit, that produces a pass with a 6.5-second margin. The engineering decision is to use the same start definition and synchronized clock in the test script, event log, and field proof, then repeat the test at the remote point. Finally, note that the 30-second basis comes from FMDS 5 to 32 when adopted by the insurer or project. It is not a universal NFPA 13 default. This section focuses on riser, floor control, and zone architecture within a data center fire protection system. The basic flow runs from the fire pump and water supply, through the main control valve and floor control assembly, to the wet, dry, or preaction valve, and finally to branch lines and sprinklers. Testing and drainage provisions are part of that same chain, not an afterthought. Zoning should match the way the facility is divided and operated. That means aligning sprinkler zones with fire compartments, floors, operational isolation boundaries, and response responsibilities. Isolation points should be safe to operate and clearly visible at the fire alarm control panel, building management system, or security operations center. Oversized zones should be avoided, because maintenance could then create an unnecessarily large outage. Field identification supports reliable response and inspection. Each riser, valve set, floor control, test valve, and drain path should be labeled, with valve charts available in both valve rooms and the fire command center. Asset tags and as-built drawings should correspond to IDM documentation. Finally, gauges, drains, release panels, and reset areas must be safely accessible, with controlled discharge for testing and drainage, consistent with NFPA 13 and NFPA 25. Sprinkler selection is not simply a matter of choosing a head that fits the ceiling. It is a listed device decision based on the hazard, ceiling geometry, airflow, obstructions, and required design density. The selected sprinkler must perform as part of the complete hydraulic and coordination design. The main parameters begin with sprinkler type, whether pendant, upright, sidewall, or a special application model. Response classification, quick or standard, must align with the protected area and the applicable code basis. Temperature rating is selected against the ambient ceiling temperature and nearby heat sources. K-factor and orifice must match the hydraulic calculation and design density, while the finish and corrosion resistance should suit both the environment and the visual requirements. In a data center, coordination is equally important. Sprinklers must work around cable trays, containment ceilings, ducts, lighting, busway, and racks. Hot aisle and cold aisle airflow should be reviewed, but never at the expense of coverage. Finally, acceptance evidence should include approved listings, hydraulic calculations, BM or reflected ceiling coordination, an obstruction walkdown, as-built head counts, and a spare sprinkler cabinet. This slide clarifies who actually decides the sprinkler selection for a data center room. The key point is that no single standard provides a universal room name to K-factor table. NFPA 13 supplies the installation and hydraulic framework, using hazard, spacing, obstructions, required flow, and pressure. It also connects sprinkler temperature to ambient conditions, but the final selection still depends on the design. NFPA 75 and NFPA 76 add important context for IT equipment and telecommunications environments. They coordinate protection and detection, but they do not prescribe one fixed sprinkler schedule. FM guidance brings in loss prevention criteria, including density, area, concealed spaces, and FM-approved applications. In every case, the project basis and the exact listing remain essential. The final authority is the actual sprinkler submittal from the manufacturer, or OEM. That documentation confirms orientation, response, temperature, K-factor, pressure, and compatibility with wet, dry, or preaction systems. So the review should begin with room risk, then move through adopted criteria and hydraulics, and finish with the specific listed product. Here, QR means quick response, PAV means preaction, and K relates flow to pressure. This room matrix translates the applicable standards into practical design decisions for data processing spaces. The key point is that the sprinkler system cannot be selected from room name alone. We first identify the actual equipment and fire risk, then apply the FM design case before choosing the K-factor or temperature rating. Rack-mounted lithium-ion battery backup units change the design basis significantly. For a standard data hall without rack-BBU, wet systems are preferred, with FM 0.10 over 1,500 square feet as the listed basis. Where rack-ion BBU is present, the design increases to FM 0.20, with larger design areas and potential use of barriers. AI, GPU, and HPC halls require the design to match the actual BBU and cable conditions, including HC2 where cable loading is high. Hot aisle containment must be protected as required within the containment. The matrix also covers raised floor and above-ceiling cable voids, where wet, dry, or preaction systems depend on the environment and extended coverage listings. Finally, temperature selection follows the space conditions. Standard ratings up to 38 degrees Celsius, and higher ratings where temperatures exceed that range. This design table classifies telecom, control, and IT support rooms according to their actual cable, equipment, battery, packaging, and storage hazards. The key point is that these rooms should not all be treated as identical. The hazard is controlled by what the room contains and how it is used. For MMR, MDF, IDF, and network rooms, the basis is typically cable and electronics, with local UPS equipment considered where applicable. Telecom exchanges require additional attention to equipment, cable, and any underfloor or ceiling spaces. NOC, SOC, BMS, EPMS, and DCM rooms are usually light hazard spaces, but consoles and room contents still need verification. Staging, burn-in, and repair rooms may become ordinary hazard areas when packaging, bench work, or charging is present, so battery risks require a specific review. Tape, media, and record rooms are different again, because commodity type and storage height determine the sprinkler design. Across the table, wet systems or approved preaction systems are identified, with quick-response sprinklers commonly used. K-factors and temperature ratings must be confirmed by calculation, room conditions, and the applicable NFPA or FM basis. This room matrix covers the main electrical distribution spaces and shows why they cannot all be treated identically. The governing factors are the fuel package, the heat profile, and the geometry of the equipment and obstructions. Electrical by itself is not a hazard classification. We still need to verify cable and plastic loading, any oil, the battery type, storage conditions, and continuous operating temperatures. For switchgear, switchboards, ATS equipment, UPS rooms, and PDU or RPP spaces, the typical screen is a wet system or an approved preaction valve arrangement, with quick-response sprinklers coordinated around cabinets and clearances. Temperature ratings and K-factors depend on the room temperature and the hydraulic design. Busways and electrical risers require attention at every level and within relevant voids, while dry transformers, inverters, and capacitors require an obstruction review and a full-load heat survey. The primary design references are NFPA 13, NFPA 75, NFPA 76, FMDS 5-32, equipment data, and the applicable battery or shaft design basis. Abbreviations on the slide help connect the matrix to the equipment you will see in the field. This design table focuses on two areas that need more than a generic sprinkler approach: batteries and oil-filled transformers. The central principle is match the protection system to the chemistry, equipment, and tested fire behavior. For lithium-ion UPS rooms, that may mean a wet system supported by approved cabinet and fire test information. Lead-acid rooms add considerations such as plastics, hydrogen, acid, and ventilation controls, with sprinkler temperature selected according to the design conditions. Storage and charging rooms are even more test-specific because state of charge, packaging, and storage arrangement can change the hazard. Rack-mounted lithium-ion battery backup units may require quick-response sprinklers, vertical barriers, and a basis tied to FM criteria. Oil-filled transformers are different again. They typically use dedicated water spray, deluge, or another approved system, with oil volume, separation, drainage, and heat exposure driving the design. The final rows cover energy storage, inverter, and capacitor rooms, where the chemistry, enclosure, and propagation behavior must be verified. Overall, this is a room-by-room screening tool, not a substitute for the applicable NFPA, FM, listing, and fire test requirements. This design table organizes the mechanical and cooling spaces that support the data center, with a focus on measuring heat and separating process-related hazards. The key point is that the protection system must be selected by the actual room conditions, equipment, combustibles, and heat exposure, not simply by the room name. Most of these spaces use wet pipe sprinklers with quick-response upright or pendant heads. Chiller, heat exchanger, thermal storage, and chilled water pump rooms are evaluated for equipment, insulation, oil, plastics, and service fuel. CRH, AHU, and FCU rooms add filters, belts, insulation, and stored spares, with careful review of ducts and obstructions. Cooling towers may require wet or dry protection depending on freeze exposure, and their combustible fill and outdoor conditions need listed applications and FM criteria. The electric fire pump room, valve and compressor areas, and lift or access equipment machine rooms each require coordination with equipment layouts, piping, hydraulic oil, and local code requirements. Sprinkler temperature ratings must follow the maximum sprinkler level ambient and local heat sources. A warm plant room is not automatically an intermediate temperature classification. The listed abbreviations identify common equipment and access systems used throughout these rooms. This room matrix focuses on generator and fuel system areas, where the protection strategy depends on the hazard, not simply on selecting a sprinkler K-factor. The key point is that fuel spray, pool fire, hot machinery, ventilation, and enclosure conditions may require foam, water spray, water mist, or another listed system. For a generator room, the starting point may be wet sealing protection, but the design must account for diesel or gas, oil, hot surfaces, and the heat plume. Containerized generators rely heavily on the listed package and the maximum enclosure ambient. Day tank rooms, transfer pumps, bulk tanks, and unloading galleries each introduce different combinations of spill, pressure, exposure, and vehicle impact hazards. That is why some areas call for special nozzles or open systems, where there is no thermal operating element, while sealing sprinkler temperature is determined through an ambient survey. The applicable basis may include NFPA 13, 30, 37, 75, and 76, along with FM criteria and approved listings. In practice, we should use the K-factor and sprinkler temperature only after the hazard, application, and system listing have been established. This design table maps occupied, circulation, and service rooms to the appropriate fire protection system and design basis. The central principle is simple. Use the actual fuel loading and room function, rather than assigning one hazard classification to an entire facility. Offices, meeting rooms, training areas, lobbies, corridors, stairs, toilets, lockers, prayer rooms, and first aid spaces are typically screened as light hazard, with wet pipe systems and quick response sprinklers. However, furniture, records, textiles, storage, ceiling conditions, and local egress requirements still need to be verified. Pantries, canteens, and kitchens require a more specific review. Seating areas may use ceiling sprinklers, while cooking and grease-producing equipment may also require a listed wet chemical hood system. Janitor rooms, housekeeping areas, and waste rooms can move into ordinary hazard when chemicals, paper, or plastics increase the fuel load. Water treatment, reverse osmosis, sewage treatment, sump, and drainage areas may need corrosion-resistant sprinklers, based on the process and its chemicals. The listed K factors and temperature ratings are common screening values, not universal room requirements. Final selections must follow hydraulic calculations, NFPA 13, NFPA 75, NFPA 76, FM guidance, local code, and the relevant safety data sheets. This slide provides the room matrix for storage, chemical, and logistics areas, with the design driven by the actual hazard and arrangement in each space. The most important concept is that storage method follows the commodity, packaging, height, rack layout, clearance, and ceiling, not occupancy alone. Loading and receiving areas may use wet or dry systems depending on climate, with protection selected for vehicles, pallets, staging, and packaging. Workshops and spare parts stores generally use wet systems, but oils, welding, and other heat-producing processes require additional review. High-piled or rack storage may need CMDA, CMSA, ESFR, or in-rack sprinklers, based on the listed design criteria. Chemical and flammable liquid rooms are treated as special hazards. Their protection depends on liquid classification, container type, spill potential, and chemical reaction, so foam, water, or another approved system may be required. Waste and temporary fit-out storage must also reflect peak pile conditions. Finally, the applicable basis comes from NFPA 13, NFPA 30, NFPA 75, NFPA 76, FM guidance, safety data, and management of change controls. This slide presents the selection logic for choosing sprinkler temperature and K factor. The key principle is select from evidence, not from the room name. We make 4 decisions. First, determine the required design discharge using Q equals D times A. Here, D is the approved design density, and A is the sprinkler coverage area. The source must be an approved NFPA or FM density, or a listed design. Second, select the K factor using K equals Q divided by the square root of P. K 5.6 or K 80 and K 8 or K 115 may be candidates. A larger K factor can reduce pressure, but it does not reduce the required flow. Third, use the maximum ambient temperature at sprinkler level. Up to 38 degrees Celsius generally points to ordinary temperature sprinklers. Above 38 through 66 degrees, intermediate temperature may be needed, with local heat conditions checked. Finally, confirm the application and listing, including quick response, extended coverage, storage, or special applications. Match response, orientation, system type, and approved use while reviewing obstructions. The selection is not ready for IFC until the record includes room risk, approved discharge, flow and pressure, ceiling temperature, obstruction review, and the exact listing. This example shows how to compare 2 FM-approved sprinkler options for a rack-mounted lithium-ion BBU before completing the full hydraulic model. We begin with the assigned coverage, 3 meters by 3 meters or 96.88 square feet. Using the design density of 0.20 gallons per minute per square foot, the required flow at one sprinkler is 19.38 gallons per minute. The pressure then depends on the sprinkler's discharge coefficient, K. For the K 5.6 or K 80 candidate, the calculation produces 11.97 psi. For the K 8.0 or K 115 candidate, the same 19.38 gallons per minute requires only 5.87 psi. The key point is that both candidates deliver the same required flow, while the K 8.0 needs 6.10 psi less at this sprinkler head. That does not by itself establish the system demand. The complete FM design area remains 2,500 or 3,500 square feet, depending on the system type, and full hydraulics, spacing, and listing compliance still decide the selection. Finally, temperature matters. Use a listed ordinary temperature QR model when maximum ambient temperature is no more than 38 degrees Celsius. This slide focuses on the visual review of sprinkler layout design in a data center. The central point is that protection must reflect the actual room configuration after installation, not just the empty design space. That means reviewing the final arrangement of cable trays, ducts, containment, racks, and support systems, because each can affect sprinkler coverage and discharge patterns. First, review dimensions carefully. Final spacing and clearances must follow the adopted standard, the specific sprinkler listing, and the requirements of the authority having jurisdiction. A generic training image cannot replace that project-specific review. Next, control obstructions. Cable trays, ductwork, containment roofs, and racks may block or redirect discharge. Where that happens, the design may need additional sprinkler heads or relocated piping. Finally, perform field proof. After fit-out and before handover, conduct a physical obstruction walkdown. Confirm that the installed conditions match the drawings, then update the drawings and hydraulic assumptions wherever necessary. The governing references here are NFPA 13, the AHJ, and FM Datasheet 5-32. This section establishes the hydraulic design basis and the evidence needed to demonstrate that the fire protection system will perform as intended. Hydraulic calculations translate the occupancy, hazard classification, and system configuration into required flow, pressure, and water supply performance. The design basis should identify the method selected for each protected area, along with the design area, density, sprinkler type, and K-factor. It should also account for hose stream allowance, required duration, the water supply curve, fire pump contribution, and an appropriate safety margin. Pressure losses must include equivalent pipe length, elevation, fittings, backflow preventers, valves, and any preaction or dry valve equipment. For a data center, I would also verify that the actual fit-out is represented. That includes high-density cable trays, storage, battery areas, electrical rooms, and any conditions that could change obstruction or hazard classification. Each isolated zone should remain adequate during maintenance or impairment conditions. The supporting record should include signed calculations, water supply and pump data, as-built routing and pipe sizes, approved sprinkler data sheets, post-installation flow or drain tests, and documented AHJ or insurer comments through closure. This slide focuses on how spatial geometry affects sprinkler performance in a data center fit-out. The key issue is that physical elements can interrupt the intended discharge pattern, even when the sprinkler system was hydraulically designed correctly. Under NFPA 13, the clearance from the sprinkler to the ceiling is typically between 1 and 12 inches. Sprinklers should also be no more than 18 feet apart, measured from deflector to deflector. Where equipment or rack tops create an obstruction, maintain at least 18 inches between the sprinkler deflector and the top of that equipment. The most important principle is to manage obstructions before they compromise coverage. Wide cable trays, ductwork, and hot aisle containment can block discharge. Depending on the geometry, the response may be to add sprinkler heads, offset their locations, or use sidewall sprinklers. Finally, this is not a one-time check. Every fit-out change, including new cable trays or containment roofs, requires the hydraulic assumptions to be reviewed again. Good change control keeps the installed system aligned with the design intent. This section focuses on piping supports, bracing, seismic coordination, and drainage, all essential to keeping the fire protection system safe, functional, and maintainable throughout the facility lifecycle. Proper structural support is required for water-filled, dry, and preaction piping, and the design must follow the adopted standard and applicable seismic criteria. Coordination is especially important in a data center. Supports must account for structural capacity, cable trays, busways, ducts, and maintenance access. We also need to avoid unsupported flexible drops or field reroutes that could invalidate the approved design. Drainage is another critical consideration. Main drains, auxiliary drains, and low-point drains should be provided where required, with a clear strategy for removing trapped water from dry and preaction systems. This helps reduce corrosion, and drain discharge must remain safe, visible, and controlled during testing. Finally, these conditions need lifecycle control. Supports should be inspected after fit-out, seismic events, major maintenance, or cable tray changes. Any pipe route change requires updated as-builts, and affected zones should be retested after support, drain, or valve modifications, in accordance with NFPA 13, the local seismic basis, and NFPA 25. This slide presents a critical architectural principle for digital fire protection interfaces. Separate life safety command logic from monitoring functions. The inputs include alarms from ASD, water flow devices, and manual stations, along with supervisory conditions such as tamper, low nitrogen, generator faults, and panel trouble. Those inputs are evaluated by the releasing panel, which applies the defined criteria and timers. That distinction matters because release behavior must follow the approved design basis. The slide specifically cautions against adding release delays unless they are formally approved. From there, the system produces two different categories of outputs. Life safety outputs go to the fire alarm control panel and include annunciation, evacs commands, and the solenoid trip. Monitoring outputs go to the BMS or SOC, where the function is limited to read-only event logging and status tracking. This means the BMS or DCM can observe conditions, but it does not become the system responsible for executing fire protection commands. In practical terms, monitoring platforms provide visibility, while UL-listed fire alarm equipment retains control of the life safety decision and action. This slide defines the required timing and sequence logic for a preaction fire protection system. The central point is that commissioning must demonstrate the complete sequence, not simply prove that individual devices can be triggered. Timing must be shown explicitly. At T+0, the detector alarm or approved release criteria begins. From T+0 to T+N, the releasing panel verifies the logic. Any delay or abort function is permitted only when it is part of the approved design. When the system trips, the solenoid and trim open the valve, allowing water to fill the piping. Sprinkler operation then produces a water flow alarm, providing field confirmation that water has actually moved. Reset is the final controlled step. It includes physical inspection, draining, valve reset, and restoring packaged nitrogen pressure. During testing, record each event time: detector alarm, release command, valve trip, water entry, water flow or pressure change, FACP, BMS and SOC events, and final reset. Use synchronized clocks before integrated systems testing. Delays, bypasses, and maintenance modes must be access controlled, logged, and restored, consistent with NFPA 72, NFPA 13, and NFPA 4. Water damage management in a data center is not about weakening fire protection. It is a disciplined process for preventing accidental discharge, limiting the consequences of an event, and recovering safely. The goal is to control water risk without compromising fire control. First, prevent accidental discharge. Use listed preaction assemblies and approved release panels, and supervise valves, low air or nitrogen, panel troubles, and power. During fit-out, protect sprinkler heads from impact. Also control hot work, cleaning, dust, and sealing work through impairment permits, while training operators on alarm stages and reset rules. Next, limit the consequence. Zone piping and valves so one incident does not affect unnecessary areas. Plan drainage or containment, identify emergency isolation tools and responsible roles, and keep floor tiles, cable openings, and rack aisles clear. Finally, recover safely. Do not restart cooling or re-energize equipment until water, smoke, and electrical risks are evaluated. Inspect the affected systems, then dry, clean, document, and retest the zone. Close the incident review with management of change actions when needed, following NFPA 25 and the owner's emergency response plan. This slide shows how I calculate the water trapped at a low point before deciding how that water should be drained. The key concept is to use actual internal pipe diameters and routed lengths, then add the verified internal volume of the collection pot, fittings, and trim. The total trapped water inventory is 14.84 gallons. The calculation has three components. The DN50 low-point branch contributes 10.28 gallons, based on a 52.5 mm internal diameter over 18 meters. The DN32 drops contribute another 3.06 gallons, using a 35.1 mm internal diameter over 12 meters. Finally, the trim and collection pot add 1.50 gallons, based on OEM or CAD data. These values come from the approved as-built or CAD route, actual pipe IDs, and verified equipment volumes. The result supports decisions about drain location, a safe receptor, and service planning. It does not size the drain pipe. Instead, the 14.84-gallon inventory is what must be controlled after a trip, using a drain arrangement compliant with the adopted NFPA 13 edition and supported by NFPA 25 inspection, testing, and maintenance criteria. This slide focuses on low-point management and auxiliary drains in dry and Preaction systems. The physical issue is straightforward. Condensate can collect at low points, including branch piping, drops, and trim. That volume needs to be calculated so the drain pot and associated handling capacity are properly planned, while pipe sizing follows the adopted NFPA 13 criteria. The baseline arrangement remains manual and listed. It includes a manual drain valve, and the discharge must go to a visible receptor so maintenance personnel can see and manage the water directly. The digital enhancement adds a water presence sensor and a normally closed solenoid at the end line. This does not replace the required drainage hardware. Instead, it provides supervised maintenance assistance through a building management system trouble alarm. The key diagnostic distinction is water presence is a maintenance trouble, not a fire alarm. The solenoid fails closed, and it is inhibited during a release, so the enhancement supports monitoring without interfering with system operation during an actual event. This slide uses failure mode analysis to connect each potential problem with its consequence and the safeguard intended to detect or control it. The key principle is every failure mode needs a defined diagnostic response, not just a design assumption. A closed control valve can make the system unavailable, so protection depends on a supervised tamper switch, lockout/tagout controls, and a clear impairment process. Loss or leakage of nitrogen pressure can cause a preaction valve trip or instability. That risk is addressed through pressure supervision, trend review of generator cycles, and low-point checks. Release panel trouble can degrade system release capability. The response includes a trouble signal, a fire watch, and management of change. A blocked sprinkler is especially serious because it can leave a shielded area exposed to an uncontrolled fire. BM coordination and a post-fit-out walkdown help prevent that condition. Finally, an open drain valve can create pressure instability. Restoration checklists, together with proof of normal status, provide the final safeguard. The overall message is that monitoring, procedures, and verification must work together across the entire system. In this section, I'm focusing on testing and commissioning for sprinkler and Preaction systems. The goal is not simply to confirm that equipment looks correctly installed. Acceptance must demonstrate that the system performs its intended fire protection functions from end to end. That includes proving the devices operate, valves move and supervise correctly, water is delivered as expected, alarm interfaces respond, and the system can be fully restored after testing. The first outcome is to translate every design function into a test case that can be witnessed and verified. For each test, we should capture the evidence needed to show what happened, including timing, pressure, flow, and the associated logs from the fire alarm control panel, building management system, or security operations center. Physical valve status is part of that evidence as well. Software indications alone are not enough. Finally, commissioning is not complete until the system is returned to a normal operating condition. That means closing bypasses and drains, and resolving or closing impairment permits before handover. The result should be a documented, functional system, not just a visually complete installation. This slide maps the commissioning path from the earliest design review through integrated proof and handover. At CXL0, the focus is on hydraulic calculations, riser layout, and the obstruction, coverage, and equipment matrix. That is where design assumptions are challenged before they become installation problems. CXL1 moves to factory and submittal review, verifying valve trim, releasing panel logic, and the supporting data sheets. At CXL2, installation quality becomes the priority. Pipe supports, labels, access, and wiring all need to be physically confirmed. CXL3 and CXL4 are the functional acceptance stages, where we perform trip tests and verify water flow, tamper, low air, and main drain functions. Finally, CXL5 and CXL6 test the integrated system, including chronological operation across the fire alarm control panel, building management system, and security operations center, while also confirming operator readiness. The governing rule is simple and important. Every failed test must be repeated after correction. A narrative explanation alone is never sufficient to close the issue. This section focuses on maintaining reliable sprinkler and pre-action protection through disciplined inspection, testing, and documentation. The goal is not simply to confirm that equipment is present, but to verify that the entire protection and monitoring chain works as intended, from the valve room to the FACP, BMS, and SOC. End-to-end signal verification is the central concept. Routine checks begin with panel status, clear access, generator cycles, valve positions, gauge readings, and pressure trends. Scheduled tests then validate main drains, water flow alarms, tamper switches, low air supervision, pre-action trips, inspector connections, and normal valve positions. Each test should include notification, confirmation of the expected signal, restoration, and documentation. After any event or impairment, the system must be inspected, repaired, reset, and retested. Restoration is complete only when valves, drains, air pressure, supervisory devices, alarms, and monitoring systems all return to normal. Records should include readings, event logs, forms, photos when required, permits, approvals, and technician observations. Finally, coordinate with data center operations, use approved maintenance windows, maintain spares and tools, and continually improve the process. This section organizes functional testing into distinct families, because each one checks a different link in the water-based protection chain. The key principle is that a successful test must verify both the physical response and the evidence that the response was communicated correctly. The main drain test establishes the condition of the water supply and the open path through the valve, while documenting static and residual pressure. The water flow alarm test goes further, confirming that activation reaches the local alarm, the fire alarm control or fire command panel, the building management or security operations system, the remote station, and the required printout. Tamper testing confirms that moving a valve from its normal position creates a supervisory signal, and that the signal clears when the valve is restored. The low air or nitrogen test checks the set point, notification, and pressure recovery. The pre-action trip test verifies release criteria, valve operation, water movement, alarms, and reset. Finally, the inspector test and drain confirm the remote test point, flow path, drain closure, leak-free condition, and correct zone identification. All testing follows NFPA 25 and the manufacturer's instructions. This slide presents an example format for a pre-action trip test, organized around 5 steps and the evidence required for each one. The purpose is to demonstrate the complete chain, not simply to make the valve operate. The test must prove release logic, valve action, signal paths, and safe restoration. First, establish and document normal conditions, including the valve, packaged nitrogen generator, fire alarm control panel, and releasing panel. Next, simulate the approved detection or release criteria, then confirm that the release panel processes the input and logs the alarm. The third step is verifying the physical trip. The solenoid and trim operate, the pre-action valve opens, and pressure changes are recorded. After that, verify that water flow or trip status, low air, tamper, and alarm signals appear at the required locations, such as the fire alarm panel, building management system, and security operations center. Finally, reset and restore the system. Confirm the drain is closed, the valve is reset, nitrogen pressure is restored, and every panel returns to normal. The actual method, live water decision, bypasses, and drainage must follow the approved test plan, AHJ requirements, and manufacturer instructions, including NFPA 13, 25, and 72. This section covers the dry pipe trip and low air test script. The purpose is to prove that the system responds correctly to pressure loss, valve operation, water delivery, alarm reporting, and restoration. Before testing, I notify operations and the monitoring center, confirm the impairment permit and drainage path, and record the normal nitrogen supervisory and water pressures. I also verify that the dry valve, accelerator, low point drains, clocks, and event logging are ready. During execution, I operate the inspector test or another approved test valve. I record the air pressure decay, trip point, and valve action, then confirm water reaches the test connection. I also verify the water flow alarm, low air supervisory signal, and all expected FACP, BMS, and SOC events. Any abnormal leakage or delayed trip needs to be investigated. Finally, I drain the system and low points as required, reset the dry valve and accelerator, and restore the packaged nitrogen pressure. I confirm all control valves are normal and supervised, close the permit, and update the IDM record. Complete documentation is part of proving the system is ready. These steps align with NFPA 25 and NFPA 13. This slide brings the integrated operations scenarios together, showing how the system should respond to different initiating conditions and system faults. The central test rule is that system state and event logs must align across all integrated systems. If they do not, the scenario must be tested again. In Scenario A, the ASD reaches its release criteria, the valve trips, the FACP and BMS record the event, and water flow is confirmed. Scenario B is more limited. A single detector creates an alarm and starts the investigation workflow, but does not provide release permissive, so water is not released. Scenario C simulates sprinkler water flow and verifies the FACP and EVAC's dispatch response. The remaining scenarios focus on abnormal conditions. A valve tamper produces a supervisory signal and an impairment assessment without evacuation. Low nitrogen pressure produces a supervisory signal and triggers leakage investigation. Finally, interface loss disables the BMS path, while the test verifies that local FACP authority remains active. Together, these scenarios validate both life safety actions and integrated system reporting. This section focuses on what happens after a sprinkler or preaction system is handed over. The central message is simple. A fire protection system is only credible when it remains operational over time. That credibility depends on more than the installed equipment. It requires regular inspection, testing, and maintenance, along with effective control of impairments, ready access to spare parts, and operators who know how to respond. We will first translate an NFPA 25 style inspection, testing, and maintenance approach into a schedule that reflects the specific assets and risks of the facility. We will then look at impairment control, including fire watch, temporary protection, and clear evidence that protection has been restored. The final focus is the operations team. Staff need practical familiarity with valves, signals, drains, trip response, and reset authority. These are the actions that determine whether a system performs as intended during an event. The outcome is a lifecycle approach that keeps protection visible, maintained, controlled, and ready after handover. This slide turns the IDM requirements into a practical lifecycle program for data center water systems. The foundation is using the adopted edition, manufacturer instructions, and site-specific risk together, rather than treating any single source as the entire program. Daily and shift awareness starts with confirming that the panel is normal, there are no supervisory or trouble signals, valve room access is clear, and any abnormal nitrogen generator cycling is investigated. Weekly and monthly activities move into documented checks of valve positions, gauges, supervisory signals, pump and pressure trends, and housekeeping. Quarterly or semi-annual work includes testing water flow, tamper, low air, alarm devices, and interfaces, as required by the adopted basis. Annual activities expand to main drain and trip testing, obstruction and condition reviews, emergency response drills, and evidence archiving. The program also has to respond to change. After fit-out, piping, panel, BMS, or valve maintenance work, the affected functions should be retested. After an event, the system is inspected, repaired, cleaned or dried as needed, reset, retested, documented, and followed by management of change updates and lessons learned. This slide presents a 6-step control process for managing fire protection impairments, from the initial request through final closeout. The key principle is that every impairment must be documented, approved, protected, executed, restored, and witnessed before it is considered complete. First, the request defines the reason, scope, affected zone, and expected duration. Next, approval requires sign-off from the responsible owner, the safety manager, and the authority having jurisdiction. Before work begins, the team establishes a fire watch, puts temporary measures in place, and issues the necessary notifications. The impairment can then be executed through isolation or repair, with visible status tagging so everyone understands the current condition. Restoration means returning valve lineups, signals, and pressures to normal. Finally, the team performs a witness retest, closes the permit, and records lessons learned. The absolute prohibitions are equally important. No undocumented closures, no bypass panels without a fire watch, and no return to normal without a witness retest. These controls create clear accountability and prevent an impairment from becoming an unrecognized loss of protection. This section presents the operator response playbook for a data center fire protection system. The key principle is recognizing the difference between an alarm, a supervisory or trouble condition, and an impairment, because each requires a different response. An alarm or water flow condition requires immediate action, not an automatic reset. The operator should acknowledge the alarm, dispatch the fire response team, identify the affected zone, valve set, and protected room, and confirm the appropriate evacuation or response actions. Field feedback and emergency status should then be verified and documented. For supervisory or trouble signals, the focus shifts to identifying the abnormal valve, pressure, panel, or circuit condition. The operator must determine whether protection is impaired, notify the responsible owner and operations manager, and establish a fire watch if coverage has been degraded. Finally, reset and restoration should occur only after the physical condition is safe and valves, drains, air or nitrogen sources, panels, and monitoring systems are normal. The reset authority, timestamp, and follow-up records must all be captured, with restoration verified against the Site Emergency Plan and NFPA 25. This section focuses on a simple but critical principle. A high-availability facility prepares for impairment before it happens. In the valve room, readiness means having the right parts, tools, safety equipment, and procedures immediately available. The most important requirement is accuracy, not just quantity. Spare sprinklers must match the correct type, temperature rating, finish, and wrench, and the cabinet count needs to stay current. Replacement gauges, tamper switches, low-air switches, and water flow devices should also be treated as site-critical spares. Valve trim supplies cover items such as solenoids, seals, gaskets, strainers, air maintenance components, nitrogen generator filters, service kits, and manufacturer reset tools. Drain and testing work requires hoses, caps, drain keys, portable lighting, barriers, and materials for controlling or recovering water. Safety readiness includes lockout/tagout equipment, warning signs, permits, communications, and safe access equipment. Finally, the documentation must be accessible where the work occurs. Keep the riser diagram, valve chart, operating manuals, test procedures, and emergency contacts in the valve room or fire command center, so technicians can act quickly and consistently. This workshop turns room-level risk into a practical sprinkler strategy register for the data center. The goal is not simply to name a system. For every room or zone, we need to connect the environment to the design decision, the interfaces that must be supervised, and the evidence that will prove the system works. Start by identifying the space, such as a data hall, support office, plant room, exposed dock, or electrical room. Then capture the conditions that influence protection: combustible load, airflow, ceiling height, freezing exposure, and water sensitivity. Those factors support the selection of a wet, dry, single-interlock preaction or double-interlock preaction system. Next, document the accepted strategy and create a point schedule. That schedule should include the control valve, water flow and tamper devices, low air supervision where applicable, release panels and drains. Finally, define the proof method, which may include hydraulic calculations, trip testing, water flow testing, obstruction walkdowns, or NFPA 25 inspection, testing, and maintenance. A complete register also assigns who owns restoration after testing or an impairment. This is the final check before the system moves through approval, installation release, and integrated systems testing. The checklist is organized around 3 readiness points: design, installation, and handover. The goal is to confirm that the system is not only designed correctly, but also installed, tested, documented, and ready to operate. For design readiness, verify that each room has an approved system type. The hydraulic calculations align with the supply test or pump curve, and sprinkler locations are coordinated with the final fit-out. Access to valves, drains, tests, and isolation points must also be confirmed, along with supervised points and the cause and effect matrix. Installation readiness focuses on listed compatible components, properly supported, braced, flushed, and pressure-tested piping, accurate labels and valve charts, tested release panel wiring and devices, and a safe drain discharge path. Finally, handover requires completed trip, water flow, tamper, low air, and drain tests, captured event records, closed impairments, ready maintenance resources, and trained operators. These checks should align with NFPA 13, NFPA 25, and NFPA 4. This assessment checks whether the key fire protection concepts can be applied to a real data center design, rather than simply recalled. The goal is to connect system selection, operation, monitoring, and maintenance. First, consider when dry pipe protection is justified and why it is generally not the default in a condition data hall. Then compare single-interlock and double-interlock Preaction Systems, focusing on how each system operates and what conditions are required for water release. The next question is about supervision. Be prepared to distinguish alarm, supervisory, and trouble signals associated with a preaction valve assembly. The design questions then move to physical coordination. How cable trays or containment roof obstructions should be addressed so sprinkler coverage remains effective. Finally, consider verification and reliability. What evidence demonstrates that a preaction trip test was fully completed and the system was restored to service? And when a preaction zone is isolated for maintenance, what impairment controls are required to manage the temporary loss of protection? Together, these questions test whether the system can be designed, monitored, tested, and maintained as an operational data center safety system. This reference slide brings together the core terms used in the sprinkler, dry pipe, and preaction system module. I'll begin with the 3 system types. A wet pipe system has water in the piping, and is generally the most reliable option when freezing is not a concern. A dry pipe system uses nitrogen-filled piping and a dry valve, although approved compressed air may be used as a project-specific alternative. It is intended for unconditioned or exposed areas. A preaction system keeps the piping dry and uses a detection or release-controlled valve, making it appropriate for water-sensitive critical spaces. The remaining terms describe system signals and maintenance activities. Water flow confirms that water is physically moving through the system, providing an alarm input and test evidence. Tamper indicates that a control valve is off normal, while low air or nitrogen identifies a low supervisory gas pressure condition. Both are supervisory signals and can trigger maintenance. Finally, IDM means inspection, testing, and maintenance. It is the lifecycle reliability program that helps verify these systems remain ready to perform when needed. This slide identifies the reference framework supporting the data center fire protection system. The central principle is always use the adopted edition, the local AHJ or DAMCR interpretation, listed equipment data, and the project-specific design basis. That keeps the design aligned with both governing requirements and actual site conditions. The technical standards listed here cover the main areas of responsibility. NFPA 13 addresses sprinkler installation, temperature selection, listings, and hydraulic design. NFPA 75 and NFPA 76 provide context for IT and telecommunications environments. NFPA 25 and NFPA 72 support inspection, testing, maintenance, alarm, and releasing interfaces. Additional standards, including NFPA 3, 4, 14, 20, 22, and 24, address commissioning and water supply connections. Adopted SNI additions and local authority requirements also apply. The second group includes insurer guidance, FM data sheets, current equipment approvals, OEM information, calculations, building and fire codes, and owner policies. Finally, approved drawings, room data, temperature surveys, cause and effect documentation, SAT and IST records, IDM records, and management of change records provide the project evidence needed to verify that the system remains appropriate over time. This module closes with a central message. Water-based fire protection in a data center is a technical, operational, and governance decision. The engineering choice depends on the environment. Wet pipe is the reliability baseline where water-filled piping is acceptable. Dry pipe should be reserved for justified exposure conditions, with careful attention to trip time and drainage. Preaction limits water entry into the piping, but introduces added release panel, supervisory, and reset complexity. The system also has to match the real facility. Sprinkler layouts should be reviewed against the final data hall fit-out, not just a clean ceiling plan. Hydraulic calculations, water supply, and valve pressure losses must reflect installed conditions. Operationally, control valves, low air, water flow, and release status need to be visible and supervised. Trip, water flow, tamper, and main drain tests provide the evidence that the system works. Impairments and bypasses require permits, temporary protection, and documented restoration. Finally, reset means physical verification, valve and air or nitrogen restoration, and event closeout. The IDM program preserves reliability after handover. This module closes with a principle that connects engineering performance to operational confidence. Protection must be verified, and operations must be restorable. Modern fire suppression is a mechatronic system, where piping, pneumatic nitrogen, and digital logic have to function as one seamless entity. That means the design must be precise, the performance rigorously testable, and recovery safely repeatable. The next step is to move beyond interior suppression demand and examine the external water supply, including fire pumps, tanks, and hydrants.